Okay, so here comes one of the harder problems on this entire set. It's a pretty robust question. I'm going to look at number 5 and hopefully number 6, depending on how long it takes me to do that first problem. So let's just see what we got going on. In number 6, this is an overwhelming problem. The kind of question that honestly, when you get asked, is just like, oh my gosh, what do I even do with this thing? So the first thing that we learned is that Descartes kind of helps us out because if we count the number of sign changes, I see 1 and I see 2. So Descartes would not just say that there is 2 positive real roots, but it's 2 or 0. Let me double check that again. 1 here and 1 there. Now Descartes would also tell us to take a look at t of negative x. And if I did that, I have a negative here, a positive here. This is going to stay positive because a negative cubed times an extra negative is a positive. A negative squared times a negative is negative. That one's positive because a negative times a negative and a positive. Well, 1, 2, 3. So this would be 3 or 1. Now that does actually make sense because if you added those together, there could be as many as 5 real roots, which matches the equation. Or there could be 3 real roots, which would leave 2 imaginaries, or there could be 1 real root, leaving 4 imaginaries. Now, I'm going to look at the possible rational roots, and again, this is just narrowing the search. So I know kind of how many I'm looking for, but what should I look for? Well, the numbers that go into 63 are 1, 3, let's see, what else goes in there? 7, 9, 21 and 63. Now, I don't think it's likely that 63 is going to be a root, but we do have kind of a laundry list of denominators because there's a lot of numbers that go into 12. So, unfortunately, we have an awful lot of answers right here, so I'd like to continue to narrow my search down a little bit. So what we can do is we can check out our bounds. And so what I know is that according to this thing, I have the number 4 is the lowest upper bound. There can be no root above the number 4. So, if we were looking at it, it's impossible for 21 halves to be a root of this because it's higher than 4. It is possible that 7 halves could be. That's within the realm of possibility. But 7 itself cannot be a root. So maybe we can narrow down a little bit because there's a lot of fractions, but there's quite a few fractions that are above the number 4. And then in a similar fashion, if we start looking for the ones that alternate signs, where like plus, minus, plus, minus, plus, minus, I think this is the one that works. So I know that I only want to look for roots between -5 and +4. So again, there's quite a few fractions that are outside of that range. Now I can narrow the search a little teeny bit further because I noticed that over here, these are all coordinates, like -4, -4,125, -3, -396, but I see right in here there's a root between -3 and -2. So when I look at my fractions up here, I might find a fraction like, for example, -7/3 is between -3 and -2. I also see one right in here between 0 and 1. Now that one sounds great, but I don't like it very much because there's a heck of a lot of fractions in here between 0 and 1. There's a half, a third, a fourth, a sixth, and a 12. There's just too many to look at. And then last, there's one more right in here between 3 and 4. Sorry that the camera is a little fuzzy right there, but notice that it went from a negative to a positive. So there's one between 3 and 4. But to be honest, I didn't really like this because I'm just seeing an awful lot of information that's going to be a little bit tough. So what I did is kind of what I've told you that we do sometimes is I went ahead and I typed it in real quick. I looked at my graph and I said, well, what I see is it looks like there right is a 1, -1 and -2. That looks like it might be -1.5. So let me try something. Let's calculate the value at -1.5. And you can see that, in fact, not only is 0 a root, it looks like 0 is that -1.5 is a double root, so it should divide in twice. We'll do that in a second. It also looks like this one is between -2 and -3, and I think that may be the one at -7/3, and in fact, it is. So what we're going to do is we're going to go ahead and try to divide this problem by -7/3. Now keep in mind that if we have negative 7/3, that means our factor is 3x plus 7. So when I'm all said and done, I'm going to divide them all by 3. Now this is a little bit of a process to go through. And so what I personally like to do is I take my calculator and I take negative 7/3 and I store that as a, because then I don't have to keep typing it. So I'm going to take 12 right here and I'm going to multiply it by that a value, and I got negative 28. I add 16 to it, and then that's negative 12, and I need to multiply that by a again. That's 28. I'm going to subtract that 133. Let's multiply by a again. It is a little bit of a tedious process, but we're going to get there pretty fast. 245. Subtract that 317, negative 72 times a. I got 168. Kind of running out of room here. Subtract 144, looking at 27. And I'm hoping, let's multiply that by a, and that's fantastic. I got negative 63, which I knew should have been the answer. Now, as I go a little bit further, remember we did say we're going to divide that number by 3 because of that leading coefficient. So this is really a 4, 4, 35. Let's see, 72 over 3 is going to be minus 24, and this is going to be 9. Now, for the sake of time, what I'm going to do is I'm probably going to actually end this a little bit quickly because 2x plus 3 was a double root. So what I'm going to do is I'm going to divide that actually 2 times on this. So I'm going to take that minus 3 halves, and I'm going to divide that out, in fact, twice. And remember, because I'm dividing it and there's that leading coefficient, I'm going to actually divide it by 2 on each time that I do that. And 1. Okay, so to make the video a little bit quicker, I went ahead and I divided each by negative 3 halves twice. Notice that I divided by negative 3 halves, that gave me this list. I divided by negative 3 halves again, it gave me this list. But that kind of went, I had that 2 twice. So I then divided each of these numbers by 4 because I had to divide by that 2 twice. Now, this leads me with the last little piece of our study. And it says, let's go ahead and come up with that factored form. So there is my linear factor. There's another couple of linear factors. And here comes my irreducible quadratic factor. And so, as you go through this thing, it asked me to do everything and kind of come up with a nice factored form. So we're going to factor your form, and it does say to sketch an accurate graph, but I don't think I'm going to bother to go through that because I think we kind of know what it looks like, and we do have a list of coordinates that's sitting over here that would allow me to take a graph like this, know where it crosses the axis, and grab a couple of extra points in the middle. Unfortunately, they are kind of large numbers like negative 1900 or negative 500. They're kind of large. So let's not worry about that in terms of the video. If you need to see that, you can ask for it in class. So number 6, and that's where I kind of am going to finish this one up. We're going to find this 4th degree polynomial that has these roots. Now, I did give you a trick in class that if 1 minus I is a root, then so is 1 plus I. And we know from class that if you add these 2 roots together, 1 and 1 makes 2, and the i's would cancel. So instead of writing a 2x, we write a minus 2x. And then if we square the coefficients, which are a 1 and a 1, because it's negative 1 and positive 1, if we square them, I get 1, and 1 makes 2. And then we have x equals 2 multiplicity 2. There we go. Now, as it stands right now, there's one extra little piece of the puzzle that says this is my polynomial, but I can actually use this to come up with that a value is. So let's go a little bit further. I'm going to go ahead and do a little bit of distribution. This would be x squared plus 4x plus 4. And as we discussed in class, I personally like to look for the biggest exponents first, which I see x to the 4th. There's a 4x cubed there and a negative 2x cubed there, so that's 2x cubed. I see a 4x squared, a negative 8x squared, and a 2x squared. So 4 minus 8 is negative 4, plus 2 is negative 2. Then looking for the x's, there would be negative 8x's there and positive 8x's there, which cancels out, which is nice. And then there's a plus 8 for our constant term. Now, the only thing left to do is figure out what the heck that a value might be. So it says if we plugged in 3, we're supposed to get negative 10. So if I plug in 3 for x, that would be 81. 3 cubed is 27 times 2 is 54. Let's see. 3 squared is 9, times 2 is minus 18, and a plus 8. And somehow that whole thing is supposed to be negative 10. All right, so that's going to be 81 plus 54 minus 18 plus 8. I got a number of 125. So according to this information, I could divide both sides by 125, and negative 10 over 125, math enter, is negative 2/25. And so my final answer would be negative 2/25 of x to the 4th plus 2x cubed minus 2x squared plus 8. And that is in pretty much standard form. Theoretically, I could multiply that out and distribute all of these fractions, but this is actually kind of a nicer way to look at that. So that's problems number 5 and 6. That was kind of the biggest video of the day. So hopefully that's helpful. I'll see you in a minute.